Okay, recording. You see the NMR screen?
Yeah.
Cool. All right. So I got an email from the president that I think you all got also, that we are going to return face to face. Yay! It's going to be really useful for this, pretty challenging course. I think this NMR stuff goes pretty nicely remotely. So we just got to make sure you guys stay on top of everything and not get behind, right? But anyway, yeah, we're moving along. Let me see, chat. Where's the chat? There's the chat. Okay. No chats yet. Okay. Which section are we on? I think the president email. Maybe it was the university president, not Biden. It was I think when was it? One second. Yeah, February 14th. That sounds right. It's a Monday, but for us it'll be the Tuesday. Yeah, that's right. Yeah, so that was the plan all along. So it looks like we're going to stick with the plan, which is great. Good for us. Okay. Let's see. All right, so we're going to get going. Okay, so we were on. Somebody asked which section were we on, and it's still, I think it's 5. It was number 5. This complex splitting topic. Okay, and it's where the n+1 rule gets a little funny. What were the 3 things we get from NMR, proton NMR? The first thing we learned was, begins with the letter I.
Integral?
Integral or integration, yeah. Yeah, and that was like the area under the curve, and that was the number of protons represented by signal. The other thing was maybe begins with the letters C and S.
Splitting.
Splitting was the third one, but yeah, that is the third one. And yet I'll say the second one we learned was chemical shift, and that was like where the signal is on the spectrum. And we're going to get better at just recognizing where those things are. And then the third one was splitting, and splitting was a thing called the n+1 rule. Like, remember the n+1 rule? It was and it splits a signal into like a triplet or a quartet, and it was the number of neighbors plus 1. The number of neighbors plus 1, right? So if there's 2 neighbors, it might be a triplet, right? Okay. And anyway, so what section 5 here is about complex splitting, and we're going to see a couple examples of this complex splitting throughout the course. And it's cases where the n+1 rule is a little funny. Remember what J was? That was also in the splitting section. J was the distance between the peaks in like a doublet or triplet, and it was measured in hertz. It's measured in hertz because normally the x-axis on the spectrum is not hertz. It's chemical shift, which is a kind of a normalized x-axis. Okay, but anyway, so for the J value is actually measured in hertz, and you can interconvert chemical shift in hertz. We talked about that. You won't have to do that in this course. You may have to do it in the lab course though. Okay. Cool. So yeah, I already talked about this as a nice example where the n+1 rule works great. Triplet, pentet. And the case where the n+1 rule doesn't work is if I look at the central CH2 and it has a different J value to the left versus the right. And when that happens, you get this thing called the complex multiplet instead of a simple multiplet. It's either simple or it's complex. Okay. And so these are real examples. Aldehydes are notorious for this. So if you have an aldehyde on one side, you frequently would get, if we look at the outside first, the outside signals, they're actually normal. They're simple, a simple triplet. But the central CH2 here, it has a different J value as it talks to the left and a different J value as it talks to the right. When that happens, it kind of turns into this, you think it would be three neighbors or two neighbors on one side, one on the other, three neighbors total. 3 plus 1, it should be a quartet, right? But it's not a quartet. It actually comes out as this thing called a doublet of triplets, or also called a triplet of doublets. It's the same idea. This is another case. On the left, it's a normal doublet. On the right, it's a normal doublet because there's a single CH, single neighbor, right? But the central one, it sees a doublet on one side and a doublet on the other, and it turns into something called a doublet of doublets. It's kind of weird. We'll see what it looks like in a second, okay? For now, aldehydes are the only thing that that do this. But funny that what's our next chapter? It's alkynes. And alkynes will also do this. So we'll see another example next chapter with the alkyne chapter when we get there. Okay. So here's one real example, 2-phenylpropanol. It happens to be a pretty ugly looking NMR, but it's okay. So we have unequal J values. So that's what we call an ugly looking NMR. It's kind of just a lot of background and craziness. Let's start on the left, and the ppm is roughly 9 or so, and that is the aldehyde. That's the D proton, okay? And it is a doublet. Well, that's nothing weird about that, because how many neighbors does the aldehyde have? The aldehyde has one neighbor, right? It has one neighbor, and what's 1 plus 1? It's 2. Thus, it's a doublet. Or actually not. D means the letter representative of the signal, but it also means doublet. In this case, though, the doublet, you can see what the doublet would look like. It's just 2 peaks, right? Does anybody from last time remember when we talked about J value? J was the distance between the peaks or whatever. What the default J is? There's usually a default J. Anybody remember what the default J was? It wasn't 2. 7. Yep. Good. Yeah, 7 hertz. So is that the default? No, it's not. There's this tiny little doublet. So that's weird. Okay. And let's keep going from left to right. All right. So then we have a bunch of protons around the 7-ish region, and it adds up to about 5 protons. What is that? In the 7 region, it's the aromatic, right? The 5 CHs. That's boring. That's not that exciting here. Okay. And then let's just jump to the other side now. The CH3, which is A, proton CH3 is A. That is also a doublet because it has a single neighbor, right? 1 plus 1 is 2. Oh, doublet. And its J value is 7. So that's a default J value. That's the normal J value, right? Okay, so now B looks, when we look at B now, which is this weird signal, it sees a CH in one direction and a CH3 in the other direction. And when it sees a CH3, it's like, well, I'm going to be a quartet, right? I'm going to be a quartet because it's a CH3, 3 plus 1 is 4, it's a quartet, right? But it also sees the next door aldehyde proton, which is a single proton, right? With a different J value, a small J value, 2 hertz. And so it's confused. And it actually gets expressed as a doublet of quartets. So basically what that means is it's like a quartet. That's a quartet, right? But every leg of the quartet is a doublet. Isn't that weird and kind of cool? So kind of cool and kind of weird, especially maybe more weird than cool because you've never seen it before. We will see it a little bit more as we go along. A doublet of quartets. And that's because B sees A, which makes it a quartet, right? Because it's next door is a CH3. And it also sees D, which is a single CH, And that makes every leg of the quartet to be a doublet. Okay, so somebody asks, C is also a doublet, and the answer is no. C is a big mess because, of course, it's 5 protons. They're all kind of on top of each other. It looks like a doublet, but it's not a doublet. That's just a coincidence that we see 2 peaks there. Of course, it wouldn't make sense that there would be a simple doublet due to C. It actually has 5 protons that are all kind of mushed on top of each other, and that's what it ends up looking like. Good question. Okay, cool. So, and this just shows that what I just showed. The structure is flipped over, but it shows like if you have a 7 Hertz coupling. 7 Hertz coupling. What does that mean? That means there's a coupling between the CH3 and the CH. A 7 Hertz, the default, and then there's a 2 Hertz coupling between the CH and the aldehyde. Okay, and that gets expressed as this crazy looking quartet of doublets, right? Quartet of doublets, or doublet of quartets, the same thing. Let me go back to the last slide one more time. So the distance between, let's look at D again. The distance between the peaks is 2 Hertz, right? And here on the right, the distance between the peaks is 7 Hertz, right? Okay, so now I'm going to go back to this doublet of quartets, or quartet of doublets. And can you imagine where there's 2 distances? There's a 2 Hertz distance and a 7 Hertz distance. So what's the small distance here? The small distance, like between 2 legs of the quartet. What do you think that is? Is it 2 or 7? Small number. So the small number would be 2, right? Of 2 and 7. If I'm looking at like a distance, that would probably be a 2. The small number. That's if I measure the distance between those 2 little legs. Of course, it's gonna be 2. It's a small number. Where would I see 7? If I wanted to, figure out, it's a doublet of triplets. Sorry, doublet of quartets. There's 2 J values, right? How would I measure 7? I would go from the first peak to the third peak. That's the easiest way to do it. First peak, not to the second peak, because that's just 2. But if I measure in Hertz first peak to the third peak, that'll be 7. Okay. I could also do the second peak to the fourth peak. There's a lot of ways you could do it, but almost always first peak to the third peak. First peak to the third peak would give you the larger number, which is 7. And how do we get 2? We go like from the first peak to the second peak. Cool. All right. We are kind of sort of halfway done with proton NMR. Now we're going on to carbon NMR. Carbon NMR is lecture number 6. This is a little easier. Now that we know proton, I would say carbon is a little bit easier because there's less crazy information present. All right, carbon NMR. Remember about carbon NMR when we talked about the, I'm recording, right? Yeah, I'm recording. I think I'm recording. Did it say I was recording? I think I said so.
Yeah, you're recording.
Okay. That C12, which is the normal isotope of carbon, has an I equals 0. That was that spin quantum number thing. And that basically meant that C12 is not active. It doesn't have any spin. It only has 1 spin state. To have NMR, you need 2 spin states, right? 2 or 3 or more than 1. So C13 does have spin because I equals 1/2. And that allows us to do C13 NMR, which is great, except for the fact that C12 is the dominant isotope. Most of our carbon in our world is not C13. However, there's enough C13 that you can do it. It does work. It's just it's dilute. There's much more C12 than C13. So C13 signals are 6,000 times weaker than proton because the natural abundance is so small. So then we remember how we introduced NMR. We said pulsed Fourier transform NMR. How we can just do pulse, 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 pulse. And if you do that, you have a very little amount of a signal, but it'll amplify because you do it so many times. I can do a carbon 13 NMR with 30,000 scans. I can do it in maybe overnight. So you don't need very much C13 because you just do a whole bunch of scans. That was that idea of Fourier transform NMR. Another interesting thing about C13 NMR was the chemical shift range is larger than protons. It's about 0 to 200. For proton, it's usually about 0 to 13, right? You remember that. The chemical shift range in proton is about 0 to 13. With carbon, it's a wider range. Okay. We also talked about the field strength and how it how it relates to the strength of the magnet. So proton, if we look at different magnet sizes, 1.4 Teslas, 2.35 Teslas, 7 Teslas. If on any NMR machine, you get a proton frequency, right? And the carbon frequency is 1/4 of that. We did mention that also. So anytime, if I measure a proton NMR at 300 megahertz on my 300 megahertz NMR, then I measure carbon NMR, it'll be 1/4. So there's this 1/4 relationship between the proton frequencies and the carbon frequencies. It's just that's the frequencies that we did all that flipping of spins and stuff that we saw for proton NMR. And that's what we're measuring is the frequencies of RF radiation, right? It's RF radiation that flip the spins. Well, we use one frequency for proton and about 1/4 of the frequency for carbon. Okay, that's just almost like a odd trivial fact. But since proton and carbon are the most common NMRs, we should be aware of that. Okay, good. Because of the low natural abundance of C13, there's a low probability of finding two C13s next to each other, right? If I have one C13 over here, the next carbon over is probably not a C13, it's probably a C12, right? So it won't talk. A C13 will not talk to C12, and it won't have that splitting concept, right? The splitting that we saw for proton NMRs. Because you'd need two C13s next to each other, and the odds of that are like 0, okay? So we don't see C13 coupling the way we saw proton coupling. However, C13 does couple to proton atoms, hydrogen atoms. So we actually do see a coupling, the concept of coupling, the N+1 rule, between a C13 and hydrogen atoms, so like your neighboring hydrogen atoms, okay? So we see this. It turns out that this may seem useful, like, oh wow, we can actually maybe figure out how many protons are on a carbon, right? It turns out to be kind of a mess, and we want to get rid of it. We'll talk about how we get rid of it in a second. It's useless information. We have other ways of getting this information. Okay, so first we're going to talk about basically C13 coupled to protons, and then we're going to see, oh, it's really messy, and we want to get rid of it. So I'll show you how we get rid of it. Okay, so this shows, like, if I have a C13 with 3 protons on it, the carbon signal is actually split into a quartet. Okay, so 4 peaks. Why? Because there's 3 neighbors. What about a CH2? Oh, 2 neighbors. 2 neighbors get split into a triplet. 1 neighbor, doublet, and a carbon with no protons just becomes a singlet. The problem is that the J values are really large, like hundreds of hertz, not just 7 hertz. And when you have these big hertz J values, everything gets kind of overlapped, and it's a mess. So I'll show you what it looks like. This is ethyl phenylacetate. This is a real carbon NMR spectrum, so your first carbon NMR. But it's kind of a mess, right? The nice thing is you can actually see, here's the aromatic region. This is 120 to 140. All of the aromatic signals are there. And we also have the ester. Remember, in proton NMR, you didn't really see an ester or a ketone because they don't have a proton on that functional group, right? So it's a little cool. One of the cool things about carbon NMR is I can actually see that ester. It's the peak around 170 here. And then we have a CH2, a CH2, and a CH3. The nice thing you can see, though, is, oh, it looks like we have a triplet, and a quartet. Triplet, quartet. Why would that be? Oh, because we have a CH2, a CH2, and a CH3, right? Triplet, quartet. The problem is how if I have a more complicated molecule, all of those are going to be overlapped, and it's going to be a big crazy forest, right? So this happens to show them distinct. But I can get rid of the couplings. I'll show you how we do that. And then you basically just get singlet. That's actually more useful because, well, everybody does that for carbon NMR. Okay, so decoupled carbon NMR. What could that possibly mean? What could it possibly mean? Maybe carbon NMR where we get rid of the proton couplings, right? And that's what we're going to do. We're going to get rid of the coupling between C13 and proton. Okay, this looks a little weird, but it's actually, I don't know, it's a theory. You don't need to know this, but how do we do proton decoupled carbon NMR? We actually, remember, NMR is based on RF radiation, like a radio frequency, and we actually can use like two different RF sources. One of them, we're going to saturate the proton frequencies. So we're going to blast the proton frequencies with proton, the frequency of proton. It's it's 4 times the frequency of carbon. And then we're going to pulse on the carbon frequency, and then we're going to acquire the C13 signal. When we do that, the CHs basically get erased. It kind of averages out, and there's no coupling. It's cool. It makes this NMR look nice. Okay, so that's the basic theory of how proton decoupled carbon NMR works. Okay, this is a simplified explanation. You don't, again, need to know the theory. Proton nuclei are saturated, and they cycle between their two spin states. When the C13 frequencies are detected, C13 nuclei see an average coupling. And basically the coupling gets erased. Somebody said, can I explain one more time? Yeah, I'll explain one more time. And then the proton nuclei are decoupled. So basically all of the coupling, the triplets and doublets and quartets get wiped away because we blast all the protons, and the protons are all excited simultaneously, and then there's none of the coupling information, and the consequence is multiplets are no longer seen. Let me first show what it looks like, and then we'll explain it one more time. So here is the top is the coupled carbon NMR. So we see all the carbons, they are split by the number of protons, right? A CH2 becomes a triplet. Another CH2 becomes a triplet. This CH3 becomes a quartet because of the neighboring protons. Look at this beautiful spectrum on the bottom. Much more clean. All of the signals are just singlets. And now we easily can, there's not going to have overlap like potentially we'd have up top. So we see the ester, the C double bond O is the ester. We see the aromatic protons, the 1, 2, 3, 4, 5, 6. Nice singlets. We see the OCH2, which is this OCH2. We see the CH2 next to the ester, which is right here. Nice singlet. We see the CH3 up there. Okay. So basically, the theory of how it works is not that big of a deal. You don't really need to know it, but essentially what we're doing is we're irradiating the proton frequencies, which is one set of frequencies, while we detect on the carbon frequencies. Okay, so it's called NMR magic. That's one way to think about it. There's a lot of magic in NMR. You guys are barely seeing the surface of the magic in NMR. And yes, we see the TMS at 0. Yep. TMS is the tetramethylsilane is our 0 point. Okay. So pretty much every carbon NMR you're going to ever see in this course, or in your future chemistry career, will always be decoupled. Everybody in the world does decoupled. Nobody does coupled anymore. And also, okay, I'll keep going. All right. The shift range, chemical shift range. Again, you never have to memorize this. Most likely, I'll just tell you now, the exams are going to focus on proton NMR. So we're just teaching you carbon NMRs to get the basic idea. But most of the problems you're going to see are actually proton NMR. We'll see it in a couple of the example problems in our lecture that use C13. But most of the hard problems you're going to have in the exams are going to be, here's a structure, here's a spectrum, figure out the structure. You can always do that with proton NMR. Okay, but anyway, what's the range? It's about 0 to 200-ish, right? 0 to 220 or something like that. So generally speaking, like alkyl kind of boring, CH3s, CH2s and stuff are around 0 to 40. Carbon with an X group on it, which is like a bromine, chlorine, oxygen, or kind of 40 to 80. Alkynes happen to be in this region too. Alkenes are a little more downfield, and they overlap with aromatic. Okay, and then we have like the kind of esters and amides and stuff are 160, 180. And then ketones and aldehydes are around 200. That's one cool thing, is you can really distinguish a ketone from like an ester by the carbon NMR. Ketones and aldehydes are always a little further down in the 200-ish, 220-ish range. This is another little chart of this. Basically, there's multiple ways we can express this. But it just kind of breaks it down into different types of carbon signals. Okay. And like I just said, kind of esters, acids, and amides are in this 155 to 185 range. Ketones and aldehydes, that's a ketone, that's an aldehyde, those are in the further downfield region, which is cool. You can distinguish a ketone or aldehyde from a ester, acid, or amide really easily. One more chart. So there's a lot of ways you can kind of express this information, right? If you look on the web, Google C13 chemical shift chart, you'll probably find 100 different ways of saying the same thing. Okay, some samples. 1-propanol, very simple molecule. 3 carbons with an OH. Here's the whole range from 0 to 200. The downfield is next to the oxygen. It's the OH right there. It's proton C, or carbon C, not proton C, it's carbon C. And then the CH2 is a little further upfield, and then the boring CH3 is the most upfield. Okay. Dimethylbutane, very boring molecule. But there's no functional groups. It's just a hydrocarbon. One of the cool things this shows, though, okay, so go back to proton NMR. Our 3 pieces of information were integration, chemical shift, and splitting, right? Splitting we just got rid of here. Integration, there's not really integration in carbon NMR. All we have is chemical shift, right? So no integration, but sometimes peaks are really big. So 3 CH3s, they're all symmetrical. Those would be a really big peak. So you can see the really big peak. So big peaks in carbon NMR are multiple carbons, right? And then really small peaks are often carbons with no protons on them. There's some weird reasons for that I'm not going to get into. But C is really tiny. Look at C. It's the tiny one. And that's called a quaternary carbon. So in terms of peak size, big peaks are maybe multiple carbons. Small peaks are maybe no CHs. And then everything else is just kind of buried in there. Okay, so we have B. C is a tiny one. D is a little bit downfield because of the electronics of the neighboring groups. A is really boring. There's nothing nearby it. It goes far upfield. So D though, being CH2s always go a little more downfield, and that's kind of why why the D is a little further to the left. Okay. Is this only true in carbon NMR? Well, okay, so TMS is tetramethylsilane. Tetramethyl. It's silicon with 4 methyls. Silicon with 4 methyls, TMS. So is it only true in carbon NMR? Well, I mean, in proton NMR, you do see big peaks correspond to multiple things, right? So we just call that with integration. Integration's numeric. This is kind of qualitative. We're like B, big peak, 3 CH3s. So integrations is quantitative. This big peak thing is kind of qualitative. That's okay, you know. And you can often figure out, oh, this signal, you know, which signal something is by the size of the peak in carbon. Bromocyclohexane. You know, so D is the peak with the bromine. Oh, yeah, it's totally downfield. Bromine, right? Electronegative. And then we got like C and B are these larger peaks. And then we have A. Oh, a little smaller. Why are C and B large? Oh, because there's two carbons, right? So the size of the peaks here kind of helps you figure this out. And of course, C is a little bit downfield relative to B. Why is that? Why is C a little bit downfield? Oh, because it's closer to the bromine. The bromine has an effect, right, through a couple carbons. That's why C is a little more downfield than B and A, right? Cyclohexanol, similar kind of thing. Cyclohexanol is just another 6-member ring with a OH on it. And which is the downfield one? It's the CH with the oxygen on it. The CH with the oxygen, that's D. CDCl3 is the solvent. I'm not going to really talk about that, but it's also weird that it's a triplet. In carbon NMR, the solvents are kind of split by deuterium, and we see this triplet phenomenon. I'm not going to get into that. That's kind of an advanced NMR topic. But that's actually, you know, TMS and CDCl3 are kind of the two standards that we see. This is the solvent that the NMR is done in. D is downfield because of the oxygen. Then we have C and A. C and A are the big, you know, two CH2s, and then B is this further one away. Okay. Cyclohexene. You know, alkene. This is I mean, the proton NMR of a lot of these would be kind of crazy. Rings and proton NMR are kind of crazy, but by carbon NMR, this is super easy, right? We got the 2 alkene carbons, as C. We got the 2 carbons next to the alkene, or B. We got the 2 carbons that are further away, A, and they're over here. So it's a relatively simple carbon NMR, right? Cyclohexanone is a ketone. Well, where's the ketone? Oh, it's a 211, just like we said. Most ketones are usually between 200 and 220, so this is right in the middle. Remember, by proton NMR, you can't directly see a ketone. We can imply it's there, and we'll show how to do that in a bit. But otherwise, C, B, and A are just C, B, and A, right? The size of the peaks helps see that, oh, 2 carbons, 1 carbon, right? And also D is small because what makes D small? The lack of protons on it, right? Carbons with no protons on them are smaller. It's just a kind of a common phenomenon. Okay. Now this just shows the proton NMR of cyclohexanone. Which looks easier to interpret? This one or the proton NMR or the carbon NMR? I would probably say the carbon looks pretty easy to interpret, right? You have a ketone, you have a couple CH2s, right? Now, sometimes proton NMR is kind of a mess, and often in that case, the carbon NMRs maybe are easier to interpret. Okay. For cyclohexanone, which spectrum is easier? Probably the carbon, right? Often ring structures are easier to interpret via the carbon NMRs. And where does the proton show the ketone? Trick question. The answer is it doesn't. but there's ways to figure it out, and we'll actually learn that. That'll be part of our, learning how to interpret or figure out chemical structures from a spectrum. Okay, but it doesn't directly show it, right? In the way the carbon is, oh yeah, 211 right there, ketone, right? How would you distinguish a ketone from an aldehyde, though? Because ketones and aldehydes are, a ketone and an aldehyde are both in that 200, 220 range, right? So how would you know, oh, this is definitely ketone as opposed to an aldehyde? I mean, I give the structure, so, but what gives away an aldehyde? Anybody know? Think about it. Not the C13 NMR, but in an aldehyde, you actually see it in the proton NMR, right? So in an aldehyde, you actually see it around 9. You see the CH around 9, right? So a peak around 9 or 10-ish in the proton NMR is usually an aldehyde. So that's how you distinguish a ketone from an aldehyde. Okay? Okay, this is a fun one. If you want to impress your friends on what you learned today, you're going to learn briefly about DEPT90 and DEPT135, which are acronyms for distortionless enhancement by polarization transfer, which is a complicated acronym, and it's a complicated NMR technique, but it's pretty easy to see. DEPT90 and DEPT135. Okay, so normal C13, everything goes upward. What these do is they allow you to figure out if you have a CH2 or a CH3 or a CH, which is kind of cool. DEPT90 only shows CHs, so everything else goes away. It's a weird, this is also NMR magic, right? Very crazy mathematic algorithm, that they just implement on every NMR machine. But we can distinguish all carbons from just CHs. And then DEPT135 is CHs and CH3s go up and CH2s go down, which is really cool if you have a complicated molecule. DEPT always eliminates quaternary. So quaternary are the things with no protons, like a ketone, ester, things like that. Carbons that lack hydrogens are not shown in DEPT. Okay. So this is ethyl benzene, simple molecule. Normal carbon, decoupled carbon NMR, everything goes up, right? You got some aromatic stuff. You got probably your CH2 right there and the CH3 right there. The CH3 is usually going to be on the furthest to the right, okay? DEPT90, what's DEPT90 going to show? DEPT90 shows only CHs, right? Remember that? DEPT90 is only CHs. What are CHs here in the molecule? Just the aromatic. These aromatic CHs. Look at that. So DEPT90 erases these two peaks. And then DEPT135 was CHs and CH3s go up and CH2s go down. And you can see that, which is cool. So often you would do all three of these. You can run a carbon, you can do a DEPT90, you can do a DEPT135, and then it'll kind of help you in your interpretation. You're like, oh, what's the CH2? Which of my signals are CH2s and CHs? Okay. One more complicated example. Strychnine. Strychnine's a complicated molecule, right? This is a cool. It's an alkaloid. I think it's used as a rat poison. It's a kind of interesting molecule. It's nice because you can purchase large amounts of it, like for to test your NMR machine, right? I have a 100-gram bottle of this just because it's so cheap to purchase, and it's a really fun molecule for kind of like testing the NMR. So here's a normal C13 NMR. Those are all the carbons in strychnine. The peak at 78 is the standard, the chloroform, right? But everything else is like all the different carbons here. How could I figure out which of these are the CH2s and CH3s? Well, are there any CH3s? You see any CH3s? No CH3s, right? But we do see a bunch of CHs and CH2s, right? And how can we figure out which of these are the CH2s and the CHs? And that would be through DEPT. So here's a DEPT90, only CHs. See how some of the signals disappeared? What are the peaks over here around 120? Well, actually, what's the peak at 180? What do you think? 180, 170, 180. Only one of these go really far downfield. which are the things that go really far downfield. Ketones and aldehydes, but there's no ketones and aldehydes. Maybe the amide, right? So there's the amide there. We got some aromatic signals and alkene signals, and those are kind of this region here. Then we got a bunch of alkyl, CH2s, CHs, and all sorts of fun stuff. So only CHs. Well, we see 4, right? 4 in the alkyl region. Where are they? Well, where are they in the molecule? Well, we have that one. That's 1. 2. There's 2, right? 3 and 4. There's actually, I see 5 of them. 1, 2, 3, 4, 5. One of these must be doubled or like overlapped or something, because you only see 4 peaks. So one of these may actually have 2 peaks buried into it. Okay. And then what happens when we do depth 135? That gives us, we have the aromatic and the alkene. That's probably the 4 CHs, the aromatic and the alkene. And then we see those CHs up here. And then what are all the new peaks that are pointing down? Those must be the, what? The last one's doubled. I think it might be doubled. Somebody said in the chat. I think it might be doubled. It looks like a little doubled. Probably doubled. But on the bottom are CH2s. How many CH2s do we expect? 1, 2, 3, 4, 5, and 6, right? Let's see how many we got. 1, 2, 3, 4, 5, 6. Cool. So that beautifully shows this cool technique of depth 90 and 135. We're probably not going to see this again in the course. I just want to introduce it as, you know, a fun, cool example of C13 or NMR magic, right? Depth is definitely NMR magic. And it is one of those techniques that if you do research at SF State, you can do this on any molecule. I mean, you synthesize a molecule in the lab. You can do a normal carbon, you can do a depth 135, you can do a depth 90 to help you figure out, you know, what's what. What are the, you know. What if you do it on water? Well, water would be really boring because there's no carbons. So water, there's no C13 NMR, right? Even if you did, you know, yeah, that wouldn't be a very exciting one. Proton, you could do a proton NMR of water, and that would be really boring too. That would be a single peak. So, okay, I think we're ready for the fun, the grand finale now. Oh yeah, which are CHs? Yeah, we can see the CHs in the depth 90, right? All of these are CHs. Which are the CH2s? Well, they're all in the bottom of the 135. Which are CH3s? Nothing, right? If there were CH3s, they would be upward in the 135, but not shown in the 90, because 90 is only CHs, right? And which are quaternaries, lacking hydrogens? Somebody said there are 3 CH3s. There's no CH3s. A CH3 would be like a line, right? Right? There's no 0 CH3s. 0. None of these are CH3s. Like that's a CH2, 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 right? C double bond O is a quaternary. There's no, and that's probably the peak at 170 down here. Okay, and that's not a CH3. No CH3s here. If in order for it to be a CH3, you would see it in the 135 going up, and not in the 90, because 90s are only CHs, right? And of course, if you look on the upward spectra, they're all the same up here, but the down ones are the CH2s. Okay. Okay, cool. Overview carbon NMR. Each different type of carbon gives a peak. That's kind of cool. That's it, right? That's all you get, really. Each different type gives you a peak. The chemical shift gives you a clue of the type of carbon. But you'd often combine this with proton. You look at the proton, you look at the carbon, and you get the information. But it's a clue as the type of the carbon. And you look at a chemical shift chart, and then that really helps. Integrals are not used, but sometimes the size of the peak tells you the number of carbons present. Splitting is suppressed. We suppress it by decoupling to give an easy to interpret spectrum. But splitting, if you had it, might tell you, oh, you have a CH2, you have a CH3, right? But we use a different technique. If we really need to figure out, oh, is it a CH2 or is it a CH3 or a CH, we don't do spin-spin splitting, we do depth. So depth would give you that information. Super cool. Okay, we're getting into the final grand finale now of using this to figure out structures. We're on lecture 7.
Slide?
There's a question?
Yeah, could you go back a slide just for a second? Please?
Yeah, 1 sec. Uh-oh, 1 sec. Whoops. Uh-oh. Sorry, 1 sec. This thing? Chart? We're back.
Yeah, that one actually. Thank you. That's
Cool.
all.
Yeah, and these are on the website, so.
Oh yeah, true.
Alrighty. Now we get to the fun. If it wasn't fun yet, it'll become very fun quickly now, because now we're going to solve problems, and this turns into a puzzle. We love puzzles. I don't know if you all like puzzles. I like puzzles. So how can we use NMR to determine a chemical structure? We haven't done that yet. We've talked about, oh, this is the carbon NMR. This is a proton NMR. How do we use it to figure out a chemical structure? The word I often use is elucidate. How do we do NMR structure elucidation? NMR structure elucidation. First thing we got to do is review degree of unsaturation. This is the end of organic 1. You all should know this. You should all have a way of doing this. If I give you a formula, you know, C6H5Br or something, be able to figure out the degrees of unsaturation. This was really a prereq topic from organic 1, but I'm going to give you the MARC simplified formula for this. Calculating degrees of unsaturation. So the way you do this is you take 2 times the carbons minus the hydrogens plus 2, okay? You divide it all by 2. And if before you do that, oxygens you ignore, halogens you add an H, nitrogens you subtract an H. So if you do this before, you'll always get the right answer. Remember also the plus 2 is actually, it's done aside from the minus H. So maybe a better way to do this would be 2 times carbon plus 2 minus H. 2 times carbon plus 2. You have to make sure you do the plus 2 outside of the H. It's not like there's parentheses around this. It's not like minus parenthesis H plus 2. Don't do that. Okay. And if you ever get UN that's fractional or like 3.5, that's wrong, right? And the meaning of UN, again, is the number of either double bonds or rings. So, okay, then the next thing we're going to do is we're going to create a table that contains the relevant information from the spectrum. So I'm going to give you an NMR spectrum, mostly focusing on proton, and we're going to make a table that says chemical shift, splitting, integration, okay? So we're going to extract that information out of the table, out of the spectrum. And then we're going to convert every row of this little table into a piece of the puzzle. Okay, we'll show this in a second. We're going to make a little table, and every row of the table will be turned into a piece of the puzzle. And then we're going to account for all the atoms in the molecular formula. And then we're going to start snapping them together, using the NMR data. Okay. Attach the substructures to generate 1 or more candidate structures, meaning, you know, structures that might be the product. And then you may have 2 candidates. You may have like, oh, I have this molecule and this molecule. Then you can figure out which one's the good one by a little more careful interpretation. So pick the candidate that's the most consistent with all the data. So this is going to be our little protocol. You should really, if you develop your own protocol, that's okay. This protocol will work every time. So some people are like, I want to do it my own way. Yeah, it works. As long as you get the right structure, it doesn't really matter how you do it. But making the little table and interpreting the table really helps. One more thing. Note on integrals before we do examples. In these examples, the integrals are determined. So I'm going to give you the integration. Makes it easy, right? I give you the integration. But remember that integrals are a relative number of hydrogen atoms. So if I say this is 2 to 2 to 3, right? That might be, oh yeah, CH2, a CH2, and a CH3. How many protons are there? 2 plus 2 plus 3 is 7, right? So this could be totally CH2, CH2, CH3, right? But unless, what if the number of protons is 14? Right? I say, oh yeah, this molecule has 14 protons in it. Then it wouldn't be CH2, CH2, CH3, it would be CH4, CH4, CH6, right? Because this is relative. Integrations are relative, it's not absolute. The way to know is to look at the molecular formula. Don't just look at these and say automatically 2, 2, 3. It could be 4, 4, 6, okay? So we'll see examples of this in a second. All right, first one. I'm gonna switch to my other webcam now. Well, actually, one second. Let me go back. One sec. You guys can start your little table, and I'll also draw my little table. Okay, so the entries in the table are going to be you have a signal around 2.5, a signal about 2.2, and a signal about 1.1 of 1H, 3H, and 6H. So let me draw it now. I have printouts of all of these problems that I'm just going to use with my webcam. So let's try this and see if it works. Okay. Do you see it? All right, there's the problem one. All right, we cool? What's our protocol? Determine UN, tabulate the NMR data, identify the substructures, generate the candidates, and pick the best candidate. So how do we do UN of that? C5H10O. What was oxygen? What was the rule for oxygen? Do we keep it or throw it away? We throw it away. Throw it away. So it becomes C5H10. Essentially, we just ignore it. And then I do 2 times carbon. We'll do the +2 right now, minus 10 all over 2. Put that +2 earlier just to avoid math issues. So it's 2 times the carbons are 5, right? 2 times 5 is 10 plus 2 is 12. 12 minus 10 is 2. 2 over 2 is 1. Okay, that's a very important, incredibly important information. Because what is the meaning of UN? The meaning of UN is either a ring or a double bond. Now, it could be a double bond to oxygen also. Okay, so now I'm gonna try to show all this. All right, so now we're gonna make a little chart. Make a little chart of our 3 signals. I do the chemical shift with a delta signal. I do H for integration, and I do S for splitting. Delta, HS. So delta, first one's 2.5. H, how many protons are in this signal? Probably 1, right? 1 proton. What's the splitting of it? Well, if you count, it's a little hard to see, but it looks like maybe 1, 2, 3, 4, 5, 6, 7, maybe 7, a septet. Might be a septet. I am actually going to just say I can't see it, and I'm just going to say multiplet. Because I could say septet, but it doesn't really matter. I'll still get the right answer. So I'm going to, but mult. Mult is kind of like, can be interpreted as a bunch of neighbors, right? And N+1 rule is neighbors plus 1. This is obviously something with a bunch of stuff around it. Mult, I just assumed to be the same thing. Okay, what is 2.2? How many protons? Probably 3. And somebody said CH3, but that's kind of stepping ahead a bit, and I'm trying to do this a little sequentially. It is probably a CH3, yeah. But I'm gonna deduce that later. Okay, and it's a what? What's the abbreviation for a singlet? Maybe a S singlet. Okay, and then 1.1, we got how many protons? 6. 6 protons, and it's a what's the abbreviation for that? It's a doublet. Cool. D for doublet. Yeah. Are we cool so far? That was make a table, tabulate. Now we're going to identify the substructures. So we're going to basically go down this little table, and we're going to convert each of these into a substructure, meaning a piece of the molecule. For the most part, we're going to look at H. We're going to look at H, and we're going to say, well, CH maybe, right? Maybe it's a CH, right? Probably a single proton, probably a CH. If it's a CH, how many other things are on that carbon? How many other things? Because carbon loves to have how many bonds to it? Total. Carbon loves 4 things on it, right? So there's a CH, that means there must be 3 other things on it, right? And I'm going to do this with little squigglies, attachment points. Squiggly, squiggly, squiggly. Cool? Now, a 3 protons on a carbon, it should probably be, and somebody said it earlier in the chat, it should probably be a something C with 3 protons on it, maybe a CH3. So if I draw CH3, how many squigglies will there be? CH3 must have how many squigglies? One squiggly. All right, we cool? And then what about the 1.1? Now, what did when we introduced NMR, we said only certain things come around 1 and maybe upwards to 2, usually. And those are, multiples of 6, multiples of 3, right? So maybe it's 6 is not going to be like a CH6. That's impossible, right? But maybe it's 2 CH3s. So we're going to interpret 6 as 2 CH3s. So I'm going to draw 2 CH3s. And both of them have a squiggly. Okay, we cool? So that's how we kind of started this. We made some pieces. Those are all pieces of the puzzle, right? Okay. Does this add up to C5H10O? Because we need C5H10O. We haven't addressed the UN yet. So how many carbons do we got here? 1, 2, 3, 4. Uh-oh, we only have 4 carbons. So we're missing a carbon. What about our protons? Do we have all our protons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's good. Okay, so we got our protons, but we're missing a carbon. We're also missing the oxygen. We have not addressed the oxygen yet, right? So this is where we can't continue yet. We're stuck in number 3, identifying substructures. We can't continue until we address that carbon and the oxygen. And maybe the UN. How could we maybe connect a carbon and an oxygen to give us a UN equals 1? Maybe a functional group. Like, what functional group would do that? Somebody said C double bond O. That's right. But remember, there's multiple C double bond O's. So we have the names of our C double bond O's. We have ketone, aldehyde, ester, carboxylic acid, amide. Maybe and it can't be an aldehyde. It can't be an aldehyde because that would have a signal around 9, right? So maybe it's begins with K, ketone, right? So now I'm going to write ketone. I'm going to draw the ketone. How do I draw a ketone? That's a ketone. Okay, now you count everything up. Now we have our C5H10O. Now we're ready to generate candidates, okay? Now we're ready to start sticking this thing together. Okay, so how do we do this? We can, this is where you can either do this the wrong way or the right way, and I'm going to try to push you guys to always do it the right way. Look for something very unambiguous, like something that just means something very, like about the attachment, because we're going to start snapping these together. Like, I don't know, doublet. What does doublet mean? What does a doublet tell you about this 2 CH3s? How many neighbors do they have? How many neighbors? The CH3s must have 1 neighbor. Oh, do we see anything with 1 proton somewhere? I don't know. Oh, the CH. The CH, right? CH3s must be connected to the CH, right? So this is usually where I try to do this with an eraser, and my pen is erasable. What I'm going to do is I'm going to redraw CH with 2 CH3s on it, right? You guys should all be doing this with a pencil and paper also. So I can just do, I'm going to just say, well, now we have a CH3 with two methyls on it. Now I get my eraser, and I say, well, let's erase. Sorry, well, the ketone's still there. Sorry. Erase the two CH3s and erase the CH because we just did that. Now, how many pieces do we have? Oh, we have two different pieces and a middle piece. You should be able to figure out what the structure is, right? It's a ketone with this on one side, this on the other, a CH3 on the other, right? Big three. Right? It's the final answer we just figured out. So I'm not drawing all the H's. Of course, this, you know, I simplified the structure. It's methyl on one side, isopropyl, which is this thing on the other side. I could draw it all out, but we solved the structure. We're happy, 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 right? Now let's keep going and try some more. And we're gonna gradually go to more difficult ones. Did anybody get totally confused by this process yet? You're gonna get better at it as we do more examples. The main thing though, we first did UN and said, oh, you know, it must be a, we didn't know if it's a ring or a double bond yet. Then we made our little table. Then we made our substructures, which are the little things with squigglies on them. Then we figured out we had a ketone. That was the critical part. Then we started attaching. And what was the most important thing that we used for the attachment? The D. Sometimes I even circle that. I'm like, oh, D. As I use information, I circle it. I'm like, that was useful, right? Did we use any of the other information? Not really. The only thing that's maybe, you know, this is definitely the right answer. The other, you know, chemical shift. What about the CH and the CH3? 2 to 3 actually does mean something. It usually, what does UN tell us again? I don't know how to I know how to calculate. I just don't know what it means. So what did it mean? We calculated one. One, it could either be one ring or one double bond. Okay, and double bond could mean either C double bond C, but more likely C double bond O. Almost all of these examples, it's going to be C double bond O. So it's a double bond. It's either one ring or one double bond. Okay, we're going to see a lot of examples. Oh, it's a double bond O, ketones and aldehydes and stuff. Occasionally, we're going to see it be like a benzene. Like what's the UN of benzene? Let's just think about that real quick. UN benzene. How many rings do we have? One ring, right? How many double bonds do we have? 1, 2, 3, right? Oh, what's 3 plus 1? UN equals 4. So that will be a very common one. It's like if you see 4, you're like, oh, it's going to be benzene, right? That's going to be a very common thing. UN1 is probably going to be a ketone. Okay, let's try next problem. I was lost in the table. You got lost. Somebody got lost in the table, I think. Is that right? Confirming what you were lost on. So the table. Well, we'll try more examples, but this is a nice, simple example. We just went left to right. I'm like, okay, well, we have a CH 2.5, single proton because of 1. Multiplet meant lots of neighbors, essentially. Of course, how many neighbors are there in the final answer? A CH with how many neighbors? Of course, it's got 3 plus 3 is 6 neighbors. So it really is a septet, right? But we got away with just saying multiplet. That's what's so cool about this. You know, if I really looked closely, I could have said, oh, it's a septet. That wouldn't have really helped me. Except maybe say, oh, septet means it's next to 6 protons. Oh, the 2 methyls would account for 6 protons. But the D told us everything, right? Essentially, the table, we just kind of went left to right through each of the signals, and we made a table. Let's try another problem, and then as we do more, you're just going to see it better, all right? Let's try problem 2. Again, these are all on the website. You can, I would do them from scratch yourself also. Okay, so first thing, what do we do? It looks like we have a nice NMR here with some signals. We don't really look at those signals first. We look at C10H12O. And we say, what do we do with the O? We throw it away. We ignore the oxygen, right? So it just becomes C10H12. We do our UN, and we say 2 times 10. We're going to do the plus 2 early. and then minus 12 all over 2. That looks like 22 minus 10, not minus 12. 22 minus 12 is 10 divided by 2 is 5. Yeah. 5. Okay. What did we just say about, if you have 4, you'd say maybe it's a benzene. Oh, what do you do if it's 5? Well, it's probably going to be a benzene and maybe something else, like a ketone or something, right? Those make sense. It's 4 of them is probably benzene. And I immediately look at 7 to 8 and I'm saying, well, that's the benzene region, right? And also, when you're doing these, it may be useful for you to have your little chart, my little proton chart, the 1 through 10. When you try these yourself, you should try them yourself. And also office hours. I love doing these in office hours. Your little chart, you'll see that 7 to 8 is usually the benzene region. Okay, so we have 5. Now we make our chart. So how do we do my chart? I'm going to say delta HS. Delta HS, okay? All right. So what's my first little region? I am actually going to look at this mess over here. And I say, well, it's 5 protons. 5 protons. I am just going to say 5, and I'm going to say 7 to 8. I'm not going to interpret this mess. I'm just going to say 7 to 8 mess. Mult. For mult means, kind of like a default. It's just a kind of a mess of stuff. I can't interpret it. It doesn't matter because we'll know what it is in a second. What's this? Septet. Where is it? 3 point what? 3.5, right? 3.5. And what is it? It's a septet. And how many protons are there? Probably 1. And it's a septet. Meaning, probably looking ahead, it's probably going to be a CH next to 2 methyls, right? And then at 1.1, big doublet of how many protons? 6. So 6, and we have a doublet, D, okay? Okay, I am going to start making my pieces now. All right, so what is this 5? What 5 protons in the benzene region? 5 protons in the benzene region. How would I represent that in a substructure? So something with squigglies on it. It's probably a benzene because it's 7 to 8. And how many things are on that benzene? Is it a mono-substituted benzene, or because how many positions are on benzene? 6, right? 6 positions on benzene. So if I have 5 of them are protons, how many squigglies are there? 6 minus 5 is 1. It's a mono-substituted benzene. How do I draw a little piece? I'm going to do it up here a little bit. It's going to be a benzene, right? With how many squigglies on it? A benzene, that's a little blurry, but it's a benzene, right? It's a 6-member ring, 3 double bonds. And it's a squiggly, 1 squiggly. What about my septet? What do I do? How do I figure out the substructure right now? All I'm doing is substructures. How many protons are on this substructure, 3.5? I'm just looking at integration for the most part here. 1 is a CH, right? It's a CH. How many squigglies are there? I'm going to draw it a little further over here just because I'm out of space. CH, 3 squigglies. 3 CH, 3 squigglies. Now I have the same situation we just did in the last problem. 6 protons, doublet, it's 1.1. It must be 2 CH3s. Okay, so how many pieces I have? I have the 2 methyls, I have a CH, I have a benzene. Does this add up to 10 carbons? I got 6 in the benzene, 7, 8, 9 carbons. Uh-oh, there's 10 carbons. What about the number of protons? How do I count? 5 here, 5, 6, 7, 8, 9, 10, 11, 12 protons. Okay, you got the protons. But we're also missing the oxygen. In the same way as the last problem, we're going to deduce that we have what functional group? Extra functional group. A ketone. It has to be. You have a C and an O. We're missing a C and an O. And we're missing a UN because we have 4 in the benzene. There's 5 total, so we have to have a ketone. So good. Okay, so I got some pieces now. Erase this benzene up here. Okay. Okay, so how do I start connecting them? What I look for some unambiguous information. I'm gonna call this thing the ketone. I'm gonna call it a mystery functional group. A mystery functional group. Because here and there we're gonna have these mystery functional groups that we have to deduce. We have to say, we figure out some substructures from our table, but then we'll have a mystery functional group that we have to figure out from our molecular formula, right? And the UN. Okay, so what's the most important piece of information? I think I see that D again, and I just say, well, that must mean one thing and one thing only. D means these guys are connected to that guy, right? Circle it. Now we connect them. I'm gonna erase and connect them all. Doublet means one neighbor on the CH3s. So they are connected to the CH. The way I can do it is just add them to the CH. CH3, CH3, erase, erase, erase. Now you should see the final answer, right? We have a ketone with a benzene on one side and an isopropyl group on the other. Yeah? See it? Benzene. There's only one way to connect them. We have one middle piece and 2 end pieces. The end pieces have one squiggly, one squiggly, one squiggly. The middle piece has 2 squigglies. There's only one way we can connect them, and that's final answer, benzene, isopropyl. And the isopropyl is just, this is a simplified way of drawing it. Of course, it's a CH with 2 CH3s. That's our final answer. Okay, I'm going to try to sneak one last problem in just to get us, ready for next time. And if you have to go, you can watch the recording. But I just want to get through one more because once you start seeing this, it just sinks in. So we'll do a quick one. All right. Okay, and I'll expedite this a little bit. All right, so we just jumped to problem 4 real quick. Problem 4. I'll give you a hint. That is UN 0. You can calculate it. UN equals 0. We're gonna have tons more of these next time. I just want to, once you get the protocol down, this is actually fun and really easy. So figure out it's UN equals 0. Okay, what's my table? Let's just do the table real quick. Delta HS. Delta HS. First one's at 3.5. H is how many? 2 protons? And it's a doublet, yeah? 2 protons, and it's a doublet. 2 doublet. Okay, and then we have 2.1 is a singlet. Singlet. It disappears. Oh, I'm sorry. Yeah. It disappears with D2O. Remember what that means? Disappears with D2O. Somebody said OH, and you're right. Yeah, this disappears with D2O. It probably is an OH. I usually write that. I just don't have very much space. But yeah, 2.1. It might say like disappears with D2O. And then we have a proton at 1.8. How many protons is it? A single proton. It's a single proton, and it's a multiplet. Crazy multiplet, we just write mult. And at 1.0, we have a big doublet of how many protons? 6. Big doublet of 6 protons. 6 and is a doublet. Okay. What do we do next? We make our table, then we make our substructures. And we do that essentially looking only at the integration. So top one is 2 protons, must be a 2 protons. 2 protons must be a CH2. Yep. So I just do CH2, squiggly, CH2, squiggly. Squiggly, CH2, squiggly. Yeah. What about this? A singlet with, oh, this is the one that disappears at D2O. This disappears at D2O. And so somebody said CH, but it's actually, this is a good hint that it's an OH. So it's actually, yeah, probably an OH. So it's a squiggly OH. Okay? Squiggly OH, all right? And then we got a CH malt again. So it's a squiggly with a CH, three squigglies and a CH. And then we got our two methyl groups. Not forgiven, somebody said. Okay, so again, 6 protons, 1 ppm, definitely 2 CH3s, right? CH3, CH3. Okay, do we have any mystery functional groups? Do we have any mystery functional groups? Well, let's just count everything up and see. Well, we have 4 carbons. 1, 2, 3, 4. Oh, good. We have 4 carbons. We have the OH. We have the oxygen. What about protons? 10 of them. 1, 2, 3. Sorry, 1, 2. That's 2 protons. 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So we have no mystery functional groups. No mystery functional groups. So, right? We didn't have to. And UN was 0. That's a good hint that there's no mystery functional groups. How do I snap this guy together? Anything that really stands out? Just because we're basically over time, I'm gonna say maybe 3.5. What does that mean? 3.5 tells you what about the CH2? 3.5. It's, if you look on the chart, there's only one thing that comes between 3 and 4, and it's protons with a carbon next to an electronegative functional group. Like, what electronegative functional group do we have? The OH, right? So this 3.5 is critical, and it means the CH2 and the OH are connected, right? So I'm gonna just write OH right there and erase the OH here. Okay. Any other critical pieces of information, like maybe the doublet and the multiplet says, oh, well, these must all be connected. So the CH must be connected to the 2 CH3s, right? Same as we've seen in the last couple problems. So CH3, CH3. Okay. Erase the CH3s. Oh, we simplified this problem now. There's 2 pieces. How do they connect? Well, the isopropyl is connected to the CH2 with the alcohol. And so just to finish this up, it's simple. There's only one answer, right? Because I connected all those things, and I basically have 2 pieces, and they must be connected. So I'm going to just draw it over here just to finish. I could redraw them and have them kind of show them get connected, but it's obviously an isopropyl group next to a CH2OH, which is there, and that's the final answer. Cool problem. Sorry for going a little bit over. I think we're going to just keep going next time, and then we're going to enter the alkyne chapter. So I'm going to do probably about, there's like 15 of these. We're probably going to do about half of them and let you do the other half. If you can practice any of these, by next time you are definitely ahead of the class a little bit. And if you can get this protocol down, then you're doing great. Okay, I'm going to just stop now. Sorry, we went a little bit over, but I think it was cool. We covered some cool stuff and we got through this protocol. So we're just going to practice the protocol a bunch and then move on to chapter 13, alkynes, next time. All right. I'm going to stop recording, and if you guys have any questions or want clarification, I'm here.